So let's talk about the EIGRP topology table and take a look at how it's structured, what it's used for, how it's built, and so we can go into it and understand what we're looking at. So what is the EIGRP topology table? Well, we've talked about that. After neighbors form relationships, peer with each other, any EIGRP updates they exchange, whether they be internal or external updates, they don't go immediately into the routing table. They go into the EIGRP topology table, and from there, the diffusing update algorithm can get a hold of them and start seeing what's best, if they should be accepted or not. Maybe they lead to a loop and all that good stuff. So, as it says here, before a router can advertise anything to its neighbor, first it has to put into its topology table its own subnets. That's sort of interesting to note that, is that when you use the network command on a router, and you say, okay, network command, match this fast Ethernet interface. That subnet on that fast Ethernet interface will actually then become an entry in your own local topology table, and it will go in there. Now we're going to see all the good stuff that's kept within each entry in the topology table. All right, so how do routes get added into the local topology table? Well, as it says here, two ways. Using the network command. So when you use the network command, any local subnets that you have that are directly connected to your own router that match the network command get put into the topology table. And then also using the redistribution command. If I've got some RIP routes that I learned or OSPF routes that I learned, and I redistribute those into EIGRP. And I know from a CCNA perspective, we never really talked about redistribution. In my videos, I sort of real high level talked about it, but just once again, in case this is foreign to you and you haven't studied redistribution yet, redistribution simply means that I'm telling a routing protocol, take some routes that you learned about in some different foreign way, convert them into the protocol you understand, and send them to your neighbors. So for example, when I did redistribute connected, I was telling EIGRP, look at all of your connected subnets, even the ones that are not included in network commands. Convert those into entries in your topology table, send them out as EIGRP routes to your neighbors. If I did redistribute static, same thing. Take any static routes you have, convert them into EIGRP topology entries, send them out as EIGRP routes to your neighbors. And we're going to have a whole section on redistribution, how you do it, and some of the caveats of doing it. Okay, so we've already looked at this, the different types of messages. Haven't really spent any time yet with queries and replies, but we'll get to that, and I'll even do a lab showing you that. So it uses update and ACK messages for the topology exchange. All right, so what is actually inside of the update? Well, it depends. It depends if I'm sending an EIGRP internal update or an EIGRP external update. Let's take a look at that. It's actually pretty interesting, the different formats of the update depending on what's in there. So I'm going to go back here to my routers are directly connected. And let's set him back to what he was supposed to be in the first place. Okay, now let's remove the network 11. Actually, let's keep it in there for just a moment. Interface loopback 0. Let's shut it down. Let's start my sniffer trace. Okay, no shut. So what we're going to look at here, we've already seen this, but we'll just review it again, is what an EIGRP internal update looks like. Okay, so here we see operational code is update for 1. And then we have internal route. And so it gives all sorts of information about it. So there's a flag that says what type of route it is, internal. And it gives the router ID of the router who's sending it. Once again, remember, this is a router that's running 15.3 that's doing this. And then we've got our various what we call vector metrics: reliability, load, delay, bandwidth. These are all the things that go into that metric formula to make up distance. Next hop is all zeros. And then down here at the very end, we've got the prefix and the mask. So that's our EIGRP internal update. Now, let's go ahead and contrast that with an external update. All right, before I hit enter here, let's go ahead and start my sniffer trace. Let's stop the sniffer trace. All right, and here is our external update. Notice some differences here. Opcode is still 1 for an update. First of all, the type is different. External route. And then we've still got all of our vector metrics: reliability, hop count, bandwidth, and all that good stuff. But what's different here? Well, if we scroll down, we have external data. This is stuff that's in addition that we didn't see in the internal update. And it says, who's the router that originated this? Who's the router that actually did the redistribution? Originating autonomous system, administrative tag. We'll talk more about tags coming up maybe today, probably tomorrow. External metric. This is interesting. Let's say this route had originally been learned as an OSPF route with an OSPF cost of 100, and then we redistributed it into EIGRP. What we'd actually see here is it would say external metric of 100. It would actually give us what the OSPF metric was before it became an EIGRP route. External protocol ID, connected route. This might say OSPF. This actually tells you what it was before it was redistributed. All kinds of good information about this route, about what this route looked like before it was redistributed. So you can see the update packet format is a little bit different between internal updates and external updates. There's really nothing new on this slide. We've already talked about this. There's no additional information I can add to this. We've already seen this several times. One thing I will mention about this is the second bullet point. When full topology table exchange is done, there is no periodic reflooding of the topology table data. Let's rephrase that. If I send you a route for the 90 network, if that 90 network stays up for the next 90 days, I'm never going to send it to you again. You're going to receive hellos from me every few seconds, but as far as I'm concerned, if nothing about that network has changed, in EIGRP, there's no reason for me to resend it to you. Nothing's changed. That's different in OSPF. We'll see when we get into OSPF that when OSPF, let's say I'm directly connected to that 90 network. I own it. I sit on it. When I create an OSPF link state advertisement for that network and I flood that link statement out, that link state advertisement out, after a half hour, after 30 minutes, it's my job to reflood it again. Now, every 30 minutes, that's nothing, right? I mean, RIP does every 30 seconds of sending out its routing update. So resending the same LSA every 30 minutes, not a big deal. But I want to contrast that OSPF does that, EIGRP does not. So this is talking about when might a network be resent by EIGRP. And we can see here a metric value might change. Obviously a link failure, the link going down then coming back up, will cause it to be resent. And if a neighbor fails, the full topology table is exchanged with it again. Other situations as well. Now, when we say when a neighbor fails, the first thing that might come to my mind is, okay, something catastrophic happened. The link went down and the neighbor failed. Something, we lost hellos due to network congestion or something. But sometimes, and we're going to see this coming up here later on, there are things as a network administrator that you might choose to do that actually cause a neighbor to bounce, and that was built into the protocol. For example, let's say you and I are routers, and I've sent you 1,000 EIGRP routes. So your routing table is pretty big, consuming a decent amount of memory to hold those 1,000 routes. Later on, I, as a router, decide, you know what? I want to do summarization. I don't think I should send you all that stuff. I want to take all those thousands of routes and shrink them down to just like 3 routes, 3 very generic routes, and send those to you. Well, if I did that, if I shrunk those down to 3 routes and I just sent them to you, what good would it do you? If you had those 1,000 routes and I'm sending you 3 more, am I really helping you in any way? I'm just making your memory even worse. So what EIGRP does is if you configure summarization on an EIGRP router, that actually causes the router to temporarily kill his neighbor relationships and then bring them back again. And that's by design. Because if I configure summarization on myself to shrink those thousands of routes down to 3 routes, and then I kill my neighbor relationship with you, what's going to happen? Once you realize that I'm gone, even if it's just for 1 or 2 seconds, you will take those thousands of routes that you learned from me and whoop, disappear, vanish, kill them. You'll delete them all. And now when the neighbor relationship comes back up, I can send you those 3 summary routes, which is what I intended. I wanted your routing table to get smaller so you could just have those summarized routes. And in order to do that, I had to kill our neighbor relationship. So as it shows you here, there are various times when a router will resend its routes again. And it might not be because something catastrophic happened. We already talked about how EIGRP implements split horizon, and we talked about what that concept of split horizon is. Once again, to recap, split horizon says I cannot send an outbound routing update out an interface if that's the interface where I received that information from. I can't reflect the same route out the interface it came in on. EIGRP uses the reliable transport protocol to send updates and ACK messages. What this is referring to is, remember, EIGRP sits right behind the IP header. It does not make use of UDP or TCP. But with EIGRP, if I send a routing update to you, it's very important to me that I know that you got it. So you have to send an acknowledgement back to me so I know you got it. Otherwise, I'm going to resend it to you. We also saw this in the sniffer trace, how on a typical multi-access segment like a LAN, like fast Ethernet, your updates will go out as a multicast. And if you've got 3 neighbors out there, you keep a record of those 3 neighbors. You say, okay, I just sent out 1 multicast update. I'm expecting acknowledgments back from all 3 of them. Oh, here comes the acknowledgement for that neighbor. Great. Oh, here's the one from this guy and this guy. Great, we're all done. I got my acknowledgments back. Now, if you don't get an acknowledgement back from a neighbor, what do? You resend the update just to that guy as a unicast. And you keep trying to send it as a unicast until the retry limit has been exceeded, which is roughly 16 times. And then you kill that neighbor relationship. Because after all, if I've sent you the same update 16 times and you never acknowledged it, even if I'm getting hello packets from you, something's wrong here. And so we need to reset that relationship. So that finishes that section. And so in the next section, we're going to look a little bit more at WAN, EIGRP across WAN, and we're going to talk about some of those bandwidth restrictions and how you get around those.